All right, hello and welcome back, ALEKS students. This is another requested ALEKS topic, so definitely appreciate that. Also, as I mentioned in my last video, I am going to be making a point to be posting these videos more often. Ultimately, the goal is to have a video for every single ALEKS topic. So if there's a video, if there's a topic out there that you would like to see me make a video of, definitely please leave a comment in the comment section below. I am planning to release new videos on Sunday and on Wednesday, so keep that in mind. So this is a ALEKS topic that's called Qualitatively Predicting Reaction Entropy. It's a really nice introduction to the concept of entropy, and we'll go through again the learning progression that we would go through here to see a few different examples and to basically work our way through until we have gotten credit for learning this topic. I think to start, it makes the most sense just to talk about entropy in general and what we're talking about. ALEKS does give us these set of rules to go through, and I think that these are obviously good. I think that there's a slightly simpler way for us to think about this. So I'm gonna go through these a little bit first, and then I'll talk about my way, the thing that I think about essentially, and then we'll look at these in terms of these as well. So let's read the rules. Rule number 1. Entropy rises when gases form from solids or liquids. So essentially what this is saying is that if you have reactants that are solids or liquids, and then you have products that are gases, that the entropy will be rising. So when you go from solid or liquid to a gas phase, then entropy would be rising. That's what that first one is saying. I think the way that it's written here is a little confusing, but we can break it down essentially that way. Rule number 2. Entropy rises when mixtures are formed from pure substances. This one again is maybe a little bit more confusing just to sort of think about, but essentially what this is saying is that when we're forming mixtures where we're going to be mixing things together, typically speaking, that's going to increase the entropy. Rule number 3, entropy rises when the moles of gases increase. This is one of the easiest ways for us to see that entropy has increased for a system. Where you go from a smaller number of moles of gas to a larger number of moles of gas. That means that there's more pieces in that puzzle, and entropy will again have increased. The way that I like to think about this, or that I break it down here, is simply this. Entropy rises when there are more ways to arrange the system. If we really get into the definition of entropy and the concept of microstates, basically the way I like to think about this is that all of the particles, in your system, all of the chemical species, all of the individual atoms are arranged in a certain way. And entropy is really just a measure of how many different ways you can arrange that system. So in a solid, there really aren't that many different ways to arrange that solid. The solid really can't be moving around too much. It is, vibrating a little bit, so on and so forth. But if you think about the freedom in a gas versus the freedom in a solid, and I'm saying freedom in terms of what the individual atoms can do in the system, obviously in the gas phase there's going to be a lot more freedom. There's a lot more ways to arrange that system versus a solid. So that's sort of the take-home message, the way that I think about it, when I'm going through these. All right, let's go ahead and jump into it and just break these down. I'll just talk through sort of what I'm seeing, what I'm looking for as we're going through these. We've given this table and we're given a chemical reaction. We're going to predict the sign. Is the entropy increasing or is the entropy decreasing? If it's not possible to decide, we'll click not enough information. And then we're also told to assume that the temperature remains constant, which obviously would change things if, in real, maybe I shouldn't say real, but in some situations, if the reaction was exothermic and giving off energy, obviously that would change things a little bit. But in any case, if the temperature is remaining constant, we're just going to be concerned about the number of moles, on the left-hand side and the number of moles on the right-hand side for a situation like this. What I'm looking at right away is just adding up 2 and 7. So I see 2 moles of this C2H6 gas, 7 moles of O2 gas. So that's 9 moles overall. Goes to 10 moles. Goes to 4 plus 6 is 10 moles of gas. Therefore, I predict that the entropy is going to be increasing in this reaction. We've got more moles of gas on the right-hand side than we have on the left-hand side. That's it. For the next one, the thing that my eyes are being drawn to right away is that we've got a solid, and then we've got an aqueous phase. And then we've got a gas on the right-hand side. So the gas on the right-hand side really is going to be taking precedent here. We're going from a solid and an aqueous phase, solution to an aqueous phase solution where the solid has now been dissolved. So going from solid into if we think about what's happening to this zinc, if you imagine you are one individual zinc here and you are stuck in a solid versus now you're able to float around and be dissolved in this solution, you'll have more ways to be moving around. Likewise, for these hydrogen atoms, now you're a gas phase, you're going to be free to move around, and fly away. All right, and let's do the last one here. So, again, I'm looking as I'm looking at these, my eyes are drawn to number one, the stoichiometric coefficients, but also number two, the phases. That's the first sort of thing I'm going to be doing just sort of at a glance. And so here, my eyes immediately went to the solid. We're going from aqueous phase to a solid phase. That's sort of the dead giveaway as well. Entropy is going to be decreasing. We're locking up this calcium carbonate into a solid phase. That's going to decrease the entropy. All right, so we got our first one. Let's go to the next one. So here we're going from a solid to aqueous phase. Obviously, that's going to be increasing the entropy. Solid is solid. Aqueous phase allows us to move around, so pretty straightforward there. This one's basically exactly the same, right? Solid here, sodium hydroxide, dissolving that into Na plus and OH minus ions. A lot more freedom, a lot more ways for these these ions to be moving around, for them to be arranged in our system. So entropy is going to be increasing. Down here, we've got 4 moles of gas going into 7 moles of gas, it looks like. So we are going to make sure we're just not making any silly mistakes here, but pretty obvious here. 4 moles of gas going into 7 moles of gas, this P4, and then 6 moles of this Cl2. So obviously that's going to be increasing as well. All right, double credit. All right, one more to go and we will be done. So here, what I'm looking at, solid, breaking into a solid. So, not too much of a change there, but then we're also giving off a gas. Therefore, the entropy should be increasing. Here, looks like we're gonna have to do some addition again. 5 moles of gas on the left-hand side. So 2 moles here, 3 moles here, 5 moles of gas goes to 6 moles of gas. Entropy is gonna be increasing 5 to 6. More ways, right? We've got more moles of gas. There's more freedom, more ways to arrange things. So pretty straightforward there. And then our last one here, we're going from 4 moles of gas. So here, 1 mole of N2, 3 moles of H2, and we're forming only 2 moles of NH3. So entropy is going to be decreasing. We've got less ways, less moles of gas to be arranging. So we'll go ahead and check that. And that's that. So hopefully that strategy of going through these rules, but really the take-home message for me is this: when entropy is rising, when there are more ways to arrange the system, and just imagine if you were one of those atoms or ions, and what sort of your environment would be like if you were stuck in the solid. What is it like to be a barium cation in this solid versus, or I guess a carbon atom in this solid versus being in a CO2 gas, like in that gas phase? What are you allowed to do? How are you allowed to move around? If there's more ways for you to do things, then you're going to have more entropy essentially. So hopefully that's helpful. Thanks again for the request, and yeah, let's do ALEKS together. Cheers.